Let's take a high-level look at how Linux starts the initial process. I'm going to start by downloading the source code of the kernel because we're going to build and make a simple demonstration. So go here to the official website of the kernel and click here on latest release. Now you can see we got the tar archive. So I'm going to go and extract the tar archive with tarxf. Now you can see we have the folder over here of Linux. So I'm going to just move this to my distro folder and call it Linux. Now before I'm going to start building Linux, make sure you have the build dependencies installed. In my case, I'm using Debian, so I have setup scripts ready if you want to use them. Over here, I'm going to put a link in the description, but basically run these scripts over here. The scripts are very simple, they just install packages from apt. Okay, now I'm going to go to the Linux folder. And let's take a look at the source code for a bit and see where we're going to inspect with a debugger. So I'm going to open here init and then main.c. And here I'm going to search for kernel init. And this is the function I'm going to put the breakpoint on. You can see that it does a couple of stuff. And over here, it starts the initial process. So we're going to take a look at what exactly happens here. Now I'm going to build the kernel and do the initial setup for kernel debugging. First thing I'm going to do is I'm going to run make and then def config. And this will set up the default configuration of the kernel. Now I'm going to run make menu config. And scroll here to the bottom. Select here kernel hacking. Afterwards, enter this option here with compiler options. And first of all, we're going to enter the debug information here. And select this option over here. Also select provide GDB scripts. Now we're going to exit. I'm using tab, by the way. And click here on yes to save the configuration. Okay, nice. Now I can build a kernel. First of all, let's check how many processors I have. So I'm going to run here nproc. And you can see I have 20 processors. So that means I can split the build to 20 jobs. So I'm going to run make with the -j. And this will make the build faster. It's going to run stuff in parallel. Okay, now I can see that the build was successful. BZ image is ready. So the kernel image is ready. Also, if you run here ls, you should see here the GDB script. Now before I'm going to boot the kernel, we're going to need to do one more thing. I'm going to need to edit .config GDB, then GDB init. And here make sure that you add your directory as a safe path for GDB. This is the directory to the Linux source code. And this is to make GDB happy with loading scripts from your Linux directory. And you can find this also in the documentation of debugging kernel and modules via GDB, right over here. After you configure this, we're ready to boot the kernel. So I'm going to start QEMU. And this will emulate a computer booting up. First flag is going to be kernel, which will be the path to the image we just built. And next thing I'm going to do is I'm going to pass in the init ramfs. What is the init ramfs? It stands for initial RAM file system. And it's basically a simple file system that is stored in memory. And the kernel will use it to load the initial process. This is the way that modern Linux distros load the first process. So I'm going to go to my distro folder. And let's create here another folder called init. I'm going to make a simple hello world init process. So I'm going to open a new C file here, call it init.c. I'll just import stdio, start the main function, and just print hello Linux. Afterwards, I'm going to spin forever. Because if you don't do this, the kernel is just going to crash because the init process has exited. Okay, let's save this. I'm going to build this using GCC with the static flag. Output is going to be init. It's important that it's static because you don't want it to be reliant on any libc. Okay, now you should have the executable here and it works. Let's see. Yep. Okay, so now I'm going to pack this into an init ramfs. using a tool that is called CPIO. And this is an archive which the kernel can read. And the way it works is that the bootloader puts this archive in a specific address in memory, and the kernel knows to read this address and read the archive from it. So I'm going to take a quick look at the man page of CPIO. And first flag I'm going to use is create to create a new archive. Second one is -h. This will be the format, and it's important that you select the new C format, because this is the format that the kernel expects. So first I'm going to include the init file, so I'm going to echo init, and pipe this into CPIO, -o to create a new archive, -h and then new C. Finally, this will go into init.cpio. And now you should have the archive over here. We can make sure it's correct by running file. And you can see it's indeed in CPIO archive. Okay, now let's go back to the QEMU flags that we just specified. And after the kernel, I'm going to specify the init rd to be the init ramfs we just built. Afterwards, a couple of more options. First of all, -s to make QEMU listen for debugger connections from GDB, which is the debugger we're going to use. -S to make the machine frozen on boot. And finally, -append, no Castler. Now what is this? So if we go here to the documentation, you can see that it tells us to turn off Castler if necessary by adding no Castler. Now Castler stands for Kernel Address Space Layout Randomization, and it's basically just a security measure, but it confuses GDB, so we're going to need to turn it off. Okay, and we're ready to boot, so I'm going to just press enter on this. Now you can see QEMU is still waiting, nothing is happening. So let's connect with a debugger. So I'm going to go to my Linux folder here and start GDB with VM Linux. And I'm going to connect to my target by running target and then remote, 1, 2, 3, 4. And this is also specified in the documentation right over here. Okay, nice. We're connected successfully to QEMU. And we can see that currently we're on this address in memory. This is actually the first address that the computer is on when it's booted. Remember that we started the computer frozen. So what I'm going to do is I'm going to put a breakpoint on kernel init, which is the function I talked about before. I'm going to enable 2E mode, so we'll have a nice graphical mode here. And finally run C to continue the kernel boot. Okay, nice. Now you can see the machine is frozen here on boot. And we got the breakpoint hit over here. So now I'm going to just run N to go to the next instruction and just go through these functions here until I get where I want. Okay, nice. This is the area that I'm interested in. First of all, if I print the value of ramdisk execute command, we can see here the path of the init process it's going to try running, which is /init. And that's good because we named our executable init, and it's in the root of the archive, so that's awesome. So if I just step here into this function, run init process, we can see it starting to prepare the arguments. So now this is printed, so if we go here to the console, you can see run init as init process. Also prepares the arguments. By the way, I'm going to show you an interesting bug that the kernel actually has. If you go and print argv init, you can see that no Castler was passed as an argument to init. And this is actually a bug. And I talked about this on the mailing list, and this is still not solved, so that's pretty interesting to know. This is a bug because parameters like this are not supposed to reach the initial process. Okay, let's continue stepping through this. Okay, nice. Now we're finally on this line, kernel execv. And this line will actually go and try to execute /init. And this is where it really starts running the initial process. So if I just step into this, you can see that now we're on the fs/exec.c file. And if we look at the parameter here, kernel file name, you can see again init here. And this is actually very useful if you have problems with running the initial process. You can just step through this function and see where it fails, where's the error. And finally, let's take a look here. Okay. Yeah, so this actually does the execution work. If we step into this, And if we take a look here at ret, we can see that this was a success. So it successfully started the init process, and now if I just let QEMU continue running with C, go back to the console here, and you'll see hello Linux.